Have you ever wondered about the intricate complexity of neural networks and why it's imperative to comprehend them? Neural networks are the building blocks of modern data science, and their complexity holds the key to their power. Imagine these networks as intricate mazes, each path representing a different calculation, each intersection a decision point. This labyrinth of connections models the way our brains work, and it's this mirroring of human cognition that makes neural networks so potent. They can identify patterns, learn from experience, and make decisions much like us. But understanding these complex systems is no small feat. Each layer, each node, each connection contributes to the overall function and performance of the network, yet the rewards of understanding are immense. A fine-tuned neural network can revolutionize industries from healthcare to finance, from entertainment to cybersecurity. So, are you ready to unravel this mystery? In order to fully grasp this, let's dive into one of the most fascinating neural networks, the transformer. The transformer, a unique type of neural network, has revolutionized the world of data science. Let's take a moment to appreciate this marvel of technology. The transformer was introduced in a research paper called "Attention is All You Need" by Vaswani and his team at Google in 2017. The authors proposed a new model architecture that eschews recurrence and convolution entirely and instead relies solely on self-attention mechanisms. This radical departure from traditional neural network architecture was a game-changer in the field of artificial intelligence and data science. So, what exactly is a transformer? It's a type of neural network architecture designed to handle sequential data like time series or natural language for tasks such as translation and text summarization. Unlike a traditional deep learning model that processes data in order, the transformer has no notion of time or sequence. Instead, it uses the attention mechanism to weigh the importance of different inputs. The transformer's contribution to the field of artificial intelligence and data science is astounding. It has played a crucial role in the development of powerful language models like GPT-3 and BERT. These models, which are based on the transformer architecture, have set new standards in natural language processing tasks, such as translation, question answering, and sentiment analysis. Moreover, the transformer's ability to process sequential data in parallel makes it highly efficient, enabling it to handle larger data sets and solve complex problems in less time. This efficiency is a key factor behind the transformer's widespread adoption in the field of data science. The transformer's impact extends beyond data science. It's being used in a wide range of applications, from automated chatbots and voice assistants to genome sequencing and drug discovery. The transformer's ability to understand and generate human language is making technology more accessible and user-friendly. Now that we've set the stage, it's time to explore the inner workings of the transformer. This journey will take us into the fascinating world of self-attention, a concept at the heart of the transformer's power and sophistication. Let's dive in. The transformer operates on a unique mechanism called self-attention. Imagine a bustling city street. Each passerby has a story, a context, a purpose. Now imagine you're trying to understand this complex scene. You'd naturally pay more attention to certain elements over others based on their relevance, right? That's essentially what the transformer does with its self-attention mechanism. Let's break down how this works. When the transformer processes an input sequence, it doesn't treat all elements equally. Instead, it assigns different weights or levels of attention to each element. This is done by calculating the similarity between different elements in the sequence. Elements with higher similarity scores get more attention. This allows the transformer to understand the context and relationships within the data. So, how does it calculate these scores? The transformer uses a set of learned parameters known as the attention weights. These weights are used to compute a score for each pair of elements in the sequence. The scores are then passed through a softmax function, which converts them into probabilities. These probabilities are used to weigh the contribution of each element to the output. Now, let's talk about the transformer's architecture. It consists of an encoder and a decoder. The encoder reads the input sequence and generates a set of context vectors. Each of these vectors captures the context around a particular element in the sequence. The decoder then uses these vectors to generate the output sequence, one element at a time. The beauty of this architecture is that it allows for parallel processing. Unlike recurrent neural networks, which process sequences one element at a time, the transformer can process all elements simultaneously. This makes it faster and more efficient. But the real genius of the transformer lies in its ability to capture long-range dependencies. In a sentence, for example, the meaning of a word can depend on other words that are far away. The transformer's self-attention mechanism allows it to handle these dependencies with ease. Now that we understand how the transformer works, let's delve deeper into the concept of self-attention. Self-attention, a game changer in the field of neural networks, is the heart of the transformer. To truly grasp its importance, let's first understand what attention means in this context. In essence, attention is a mechanism that allows the model to focus on different parts of the input sequence, much like how we humans pay attention to different parts of a conversation. Now, self-attention is a special type of attention mechanism. The term self here refers to the fact that the model is paying attention to different parts of itself, that is, its own input sequence. It's like reflecting on one's own thoughts. This capacity to self-reflect allows the model to understand the context and the relationship between different parts of the input sequence. Imagine reading a novel. To understand the plot, it is important to remember what happened in the previous chapters. This is exactly what self-attention does. It allows the model to look back at the previous parts of the input sequence, understand their context, and make sense of the current part. The beauty of self-attention lies in its ability to weigh the importance of different parts of the input sequence. It decides which parts to focus on and which parts to ignore. It's like a spotlight, highlighting the important parts and dimming the rest. This selective focus helps the transformer to make accurate predictions. Moreover, self-attention is computationally efficient. Unlike other attention mechanisms, it doesn't require the model to process the entire input sequence at once. Instead, it processes different parts of the sequence in parallel, making it extremely fast and efficient. So why is self-attention critical for transformers? The answer lies in its ability to handle long sequences of data. Traditional neural networks struggle with long sequences, but transformers, with their self-attention mechanism, handle them with ease. This makes transformers ideal for tasks such as machine translation, text summarization, and many more. With a clear understanding of self-attention, we can now see why transformers are such powerful tools. Transformers and their self-attention mechanism hold immense potential in the world of data science. So what have we learned today? Let's recap our journey into the realm of transformers, a sophisticated type of neural network, and their intriguing concept of self-attention. First off, we discovered that transformers are not your average neural network. They've been designed to handle complex tasks with an impressive level of sophistication. Instead of processing data in a sequential manner like their counterparts, transformers process all the data points concurrently, making them incredibly efficient. Moving on, we took a deep dive into the inner workings of these transformers. We learned that they are composed of an encoder and a decoder, working in tandem to transform input data into output data. The encoder captures the context of the input data, while the decoder generates the output data based on this context. This intricate dance of encoding and decoding is what makes transformers so powerful and unique. Then we grappled with the concept of self-attention, a mechanism that allows transformers to assign different importance to different data points. In essence, self-attention enables a transformer to give more weight to the data points that are more relevant to the task at hand and less weight to those that are not. This capability to focus on the most pertinent information is what allows transformers to excel in tasks such as language translation and sentiment analysis. And let's not forget the attention mechanism itself. This is the secret sauce that enables the self-attention mechanism to work its magic. It assigns scores to different data points based on their relevance, and these scores are then used to compute a weighted sum that forms the output of the self-attention mechanism. So there you have it, a whirlwind tour of transformers and their self-attention mechanism. It's a complex and intriguing subject, but one that holds immense potential for those who are brave enough to delve into its depths. With this knowledge, you're now equipped to delve deeper into the fascinating world of neural networks and their applications.